Welcome to YouTube videos meant to accompany the notes uploaded for Monday the 30th. This is going to look a bit like what we did on Friday, however the approach is going to be different. There we were doing integration to solve our indeterminate structures. Today we're going to be using superposition. So this first video is going to cover the boundary conditions, how we're breaking up our problem into two pieces, and then our shear and moment functions. We've established last week how to determine the reactions of indeterminate structures by applying the boundary condition that the deflection at particular points that have boundary conditions for the deflection has to be obeyed, giving us an extra equation. This is perfectly fine the way that we approached it last week, using integration over and over again over the whole thing is perfectly fine and will work. However, there's another approach, and that is to use superposition. Right? So we've already established in the past, when we've talked about moment and shear and the internal forces and internal moments, that if we have something, if we've got a problem that looks just like the example problem we had for last week, where we had two rollers and a pin and a distributed load all across it. We turned that last week, and we said that was the equivalent to this, with reactions here, here, and here, and the distributed load, still present. This is equal to the sum of these two states, right? The results will be the same if we just look at a simply supported, uniformly loaded beam. Let's call that point A, that point B, and that point C, just like we did last time. I'll just see right there, the B is just right in the middle. Nothing special about B in this case. And then we have our reactions here. And then we just add to that this simply supported beam loaded in the middle at B. We sum these two things, we get the same behavior. So we just need to subject that to y at point B has to equal 0. And that's going to be equal to the deflection of this one at B plus the deflection of this beam at B. Right, so effectively what we're doing is we've got this problem, we're going to ignore this reaction at B. We're just going to look at what happens there, and then we're just going to take a load and just sort of shove B back up to where it was at the start. Just going to push it right back up till there's no deformation there at all. So let's call this beam uniform, and point. So then this is the deflection of point B for the uniform beam plus deflection at point B for the point beam. So if we add those deflections up, they have to be 0, and whatever force we get for B that gets us that deflection of 0, that's going to be the reaction of B. So let's solve this problem using this approach of superposition. Should be slightly easier this time. We're working on the same problem as before, but now we're breaking it down into two pieces. This one and this one. Now we do need to consider them completely separately. We do need to consider the deformation at point B due to this distributed load completely separately from this deflection at point B from this load, and then at the end we'll set them together. We'll sum them together and apply the boundary condition that the deflection at point B is 0. So we do need to have two completely separate things here. I think that you can easily, by symmetry, tell me that the reaction at A and C for both of these are by symmetry going to be 1/2 of this and 1/2 of this. So for this one, AY is going to be equal to 6 feet times 1 kip per foot. Turns out that's 6 kips, which is also going to be CY. And over here, AY, that's going to equal CY, and it's going to equal BY divided by 2. So when we look at the shear diagram for this one, let's just go ahead and draw that. We're going to pop up 6 kips. We're going to we're going to have a slope of -1. We're going to pass through 0 at point B. That's convenient. And we're going to end up at -6 kips right there, and then pop back up to 0. So we're going to have our shear function. That's a function of x. Is going to be 6 kips minus 1 kip per foot times x. We only need one x function for the whole length of this. Very good. Our shear diagram is going to be similarly very, very easy for us here. We're going to have, it's going to pop up to 1/2 BY, or I guess we could, let's have BY popped up there. Let's make that negative, huh? We know that BY is going to be positive, right? Come on. So let's go ahead and make that be negative. In which case that's negative up till we hit B, at which point it pops up to positive 1/2 BY, and then negative. So negative BY halves BY halves there. So there's our shear diagram. We are going to have two shear functions for this, right? There's a clear discontinuity from the point load BY. So from A to B, our shear function is, and function's a bit generous, right? Negative BY over 2. And then from B to C, our shear function is going to be positive By over 2. Cool, cool, cool. Now, moment, let's go back over to here, because if we're going to get our deflections, we're just going to have to keep on integrating. All right, so the moment for this one, for the distributed load, the uniform load, right, is going to be 6 kips times x minus 1/2 kip per foot times x squared plus some constant of integration, C1. But, come on, that's a pin. We know what that is. That's 0. Right? Must have a 0 moment at A, and if that is the case, well, then we better not have any constant right there. So we've got that. For this, similarly, the moment from A to B is going to be negative By over 2 times x. And I didn't even write down the constant of integration. There's a constant of integration. Sure, it's got to be 0 for the same reason that it's 0 right there. But at B, the moment is going to be the moment at 6 feet, and it's going to be negative By over 2 times 6 feet. It's going to be negative 3 By times feet, or negative 3 feet times By, I guess would be a sensible way to say it. So that's going to be our moment at B, and we're going to have to use that as our constant integration for the second portion. So from B to C, the moment, and I'm going to restart. I'm going to have x2. X2 starting at B. I think that's just going to be easier. And we're going to have negative 3 feet times By, because that's got to be the moment when x2 is 0, plus By over 2 times x2. And we can go ahead and check to make sure that we've done this correctly, that we don't have any moment at point C by popping 6 feet in for x2, and we're going to end up with 0 for this equation, which is good. We're obeying that boundary condition right there that the moment at C has to be 0. So good on that. Not a good camera angle for giving a thumbs up. So that's going to be for this one. Our moment diagram is going to look a bit like this. I'll probably give up drawing the rotation diagrams. Those don't tell you all that much. And for this one, it's going to look like this, all linear. No, you can't see that, but it's the derivative of that, or the integral of that, excuse me. Now on to finding the rotation using these moments.